everyone! In this video, we're going to be going over question 4 of the Spring 2021 Data 100 final. For part A, suppose we are modeling the number of calls to Mangobot food delivery service per minute. We believe that there are likely more calls around lunchtime. Which of the following feature encodings of the time of day, 0 to 24, exclusive of both ends, would capture this assumption and select all that apply? Okay, so if we want to make a plot that shows that food delivery occurs more often around lunchtime, it would look something like this, where we have a plot from 0 to 24 on the x-axis, and then we should have a spike around lunchtime, which is 12 in the middle, so something like that. Okay, so for each of the options given, we basically want to see whether that plot matches this plot that we want here. And for this exam, it was completely open notes, open computer, so you would be able to plot each of these different plots. But I can just draw them out of what they would look like after you've plotted them. So for the first one, time of day squared, it would look something like this, where based on the time of day, the greater the time of day, because we're squaring it, the greater the number of calls. But this isn't true because we said that we want more calls around 12, but then at the other times, especially 0 and 24, the amount of calls should be lower. So time of day squared would be incorrect. Then for the next one, the log of 12 times time of day. This looks something like this, which also doesn't match what we want in our graph, so this is incorrect. Then for 1 minus the cosine of pi times time of day divided by 12, this graph looks something like this. And we can see that this is a pretty good match with the graph that we want. There is a increase near the center of the graph, so around 12, and then it decreases back to 24. So this would be correct. And then for the fourth option, when we have e to the power of negative time of day minus 12 squared, this one looks something like this, where we have a smaller peak in the middle, but it's still a peak around 12. And we never specified what the calls were like around like 0 and 24. We just know that it should be greatest at 12, and this graph matches as well. So option 4 would also be correct. Okay, moving on to part B. Recall that in a binary classification task, we want our data to become linearly separable so that we can maximize the performance of our classifier. In many cases, however, our data are not directly linearly separable. As a result, we want to apply some transformation to our data so they will become linearly separable afterwards. For the following dataset, select all transformations that can make the data linearly separable. Okay, so again for this problem, because this test was open notes and open computer, you could plot these points and make these transformations on some graphing website like Desmos, and then see if your data becomes linearly separable. But we can quickly draw what each of these transformations would look like and then see if our data becomes linearly separable after we apply the transformation. So for the first option that we have here, we're squaring x1. So if we just look at each of our points, for example, this point here, we have negative 2, 1. If we apply the transformation, this becomes 4, 1, because we're squaring x1, which is negative 2, and negative 2 squared is 4. So we get a new point here, 4, 1, and I'm just going to cross out this point because this point would no longer be there. Then for this triangle point, we get negative 1, 1, and if we apply the transformation, we get 1, 1. So it'd be this triangle point here. So we no longer have that point. Then for this red point here, we have negative 1, 2. Squaring out, we get 1, 2. So we get this point here, and we no longer have this point. Then for this triangle point here, we have 0, 2. This still just remains as 0, 2. Then for this red point up here, it's 0, 3, which still remains as 0, 3. So we still have this point up here. And then for this point here, we have 2, 1. This becomes 4, 1. And this is just going to be this point over here. And we can see that with our new drawings out, we can draw a line through our plot to separate the triangles from the circles. So this means that our data does become linearly separable, so the first option is correct. Okay, so now moving on to the second option. So we can do the same exact thing and just apply our transformations. So I'm starting at this point here, negative 2, 1. The transformation is now squaring x2, so we have negative 2, 1 again. So this point remains. Then for this triangle point, we have negative 1, 1. This still just stays as negative 1, 1. Then for this point here, we have negative 1, 2. this will become negative 1, 4. So it would be maybe some point up here. And then for this point, we have 0, 2. This will become something like 0, 4. So something up here. And then for this point, this will be 0, 3, which will become 0, 9. Maybe some point up here. This is definitely not drawn to scale. But then for this point here, 1, 1 still remains as 1, 1. For this point here, we have 1, 2. This becomes 1, 4. So a point up here. And then for this point here, we have 2, 1, which just stays at 2, 1. So this point here. And we can see that our data still isn't linearly separable, because no matter how we decide to draw our straight line through, we can see that we still have points that are different on one side together, and this side as well, points that are different. So our data still isn't linearly separable, so the second option is incorrect. Okay, moving on to the third option. This is when we're squaring both x1 and x2. So again, starting with negative 1, 2. If we square it, this will become 4, 1. So this point over here. And something to notice with this transformation is that because we're just squaring both x1 and x2, the points that are reflected across the y-axis, so here, across x is equal to 0, they're going to land in the same places. For example, negative 2, 1 and 2, 1 will both just become 4, 1. So we can just cross out these two here because we know that they're going to become this point here. Then for this triangle, we have negative 1, 1. This will just become 1, 1. And then for this circle, this is negative 1, 2. This will become 1, 4. So some point up here. Same thing with this point. This 1, 2 is just going to become 1, 4. And then we have this triangle here, which is 0, 2. This will become 0, 4. So some point up here. And then this point is 0, 3. This will become 0, 9. So some point up there. And we can see that we can indeed divide up our data. Sorry, this should be a triangle. We can split up our data with a straight line like that. And all the triangles are on the bottom and all the circles are on the top. So option 3 would be correct. Okay, and now if we look at the fourth one, we're basically swapping x1 squared and x2 squared to now be x2 squared and x1 squared. So looking at our original drawing, if we just swap the points, so for example, with this triangle here, this is at 0, 4, now it would be 4, 0, so maybe some point over here. And then for this point here, this is 0, 9, now it's 9 zeros, so it'd be some point here. For this point, this is 1, 4, it become 4, 1, so maybe some point over here. It would just be this point here, but I'll just draw it like that. So 4, 1, and then this original point here, which is 4, 1, now we're swapping it, so now it will be 1, 4, so it'll be this point over here. And we can see that our data is still linearly separable. We can still draw a straight line through, like so, like this, to split our data. So because of that, the fourth option also works. Okay, moving on to part C. One way to transform textual data into features is to count the frequencies for all of the words in the text. Consider the following pre-processing steps. So 1 is to remove all punctuations, then remove all stop words, and note that stop words do not include words that negate things such as no or not. Lowercase the sentence and keep words that only consist of letters A through Z, and encode the sentence as a vector containing the frequencies of all the unique words in the text. Suppose we use the frequency vector from the steps above as our feature to train a logistic regression model that predicts the sentiment of a sentence, so either positive sentiment or negative sentiment. In 1 to 2 sentences, describe a case where our model would fail and make a false prediction. Okay, so I think the answer key for this question has a pretty good example. And the example they give is 2 different sentences that have the exact same words but in different orders. So the first one is, I am happy that it does not rain today. And just reading the sentence, we can tell that it's a positive sentiment. But we have a second sentence here which has the exact same words as the first one, but in a different order. It's, I am not happy today, or I am not happy that it does rain today. And we can tell that this is a negative sentiment and not positive. But based on our algorithm, all we're doing is taking away the stop words and then lowercasing all the words and then counting the number of times that they appear. And we're going to get the same vector that contains the frequencies for all of the unique words for both of these sentences because we're just simply counting up all of the unique words that appeared in our sentence. And it doesn't take into account the order, which can change our sentiment. So because of this, the frequencies will lead us to believe that these two sentences have the same sentiment when they don't. So we're going to have a false prediction for the sentiments of these sentences. Okay, moving on to option D, or part D. Recall that in the housing assignment, if we want to include a categorical variable in our linear model, we need to convert it into a collection of dummy variables of values 0 and 1. Suppose we have a data frame housing that contains a subset of the Cook County data. We are interested in one-hot encoding the categorical variable floor material and using the dummy columns as the sole features to build an ordinary least squares model to predict the sale price of the houses. Specifically, we create the design matrix X with the following block of code. So we get that floor material, and then we get our design matrix after we one-hot encode it. So in addition, running the code housing floor material.value counts gives us the following output. So remember, value counts will return a series counting the number of times that every unique value in our column occurs. So this means that for our data set, we had 50 houses that had a wooden floor material, 40 houses that had a marble floor material, and then 30 houses that had another type of floor material. So which of the following statements are true about the design matrix X, and select all that apply. Okay, so for the first option, X has a dimension of 3 columns and 120 rows. So this is correct because the number of columns that X has is the number of one-hot encoded columns of floor material, and we know that floor material has 3 different materials, wooden, marble, and other, so it would have 3 columns. Then for the number of rows, this would be how many data points that we have, and we can simply just add up the number of counts for every single material to get the total number of data points. So it's 50 plus 40 plus 30, and this is equal to 120, which matches with the 120 rows in option 1. Then for option 2, we can add a bias column of all 1s to X and still find a unique solution for the optimal parameters. So this is false because if we add a bias column to 1, then X is no longer full column rank. It has linearly dependent columns because recall that with a regular one-hot encoding, if we don't add a bias column, we're going to get something that looks like this, where every single column out of our 3 columns here is going to have a value of 1. Because that 1 represents our house having a specific type of flooring. But if we decide to add in a bias column, we can see that we can just form this bias column by adding up these 3 columns together. So because we can form one column from the other columns in our matrix is no longer linearly independent. And if our matrix is no longer linearly independent, then X transpose X is no longer invertible. And we can't find a unique solution for the optimal parameters. Okay, moving on to option 3. X transpose X is a diagonal matrix, so 0 is everywhere except along the main diagonal. So this is true. X transpose X is a diagonal matrix since the vectors in our matrix X are orthogonal. This is just the definition of our matrix when we one-hot encode columns. So it looks something like this, where we have 50, 40, and 30 along the diagonals, and everywhere else we have zeros. Then for the fourth option, all of the entries in X transpose X add up to be 120. This is also true. If we just look at X transpose X and we add everything up, we can see that we're just adding up 50, 40, and 30, which is 120. Then for the fifth option, the optimal parameter vector data contains the average sale price for each type of floor material. So this is also true. So recall that our normal equation to solve for optimal data, this is equal to X transpose X, and then we take the inverse times X transpose Y. So if X transpose X is equal to this matrix, then its inverse is just 1 over 50, 0, 0, 0, 1 over 40, 0, and 0, 0, 1 over 30. Because it's a diagonal matrix, so the inverse is just doing 1 over all the non-zero entries. Then if we multiply this matrix by X transpose Y, X transpose Y is currently a vector, and it holds for every single entry, it holds the total price. It holds the total price of the houses for every single type of material. So this first element in our vector here would be adding up the total price of all the houses with a wooden material. And then the second element would be adding up all the prices for the houses with a marble material. And then you can imagine the third element would be adding up all the prices of the houses for materials of a different type. And if we multiply this vector with this x transpose x, the inverse, this is just us adding up the total price of, let's say, this first element, all the wooden houses, and dividing by the total number of wooden houses that there are. And this is just simply the mean of the prices of all the wooden houses. Then same thing for the second element, we're adding up all of the total prices of the houses made with a marble form material, and we're dividing it by the total number of marble houses that they have, or that we have in our data set. And this is just taking the average of the price of all the houses with a marble form material. And the same thing for the last element, the other. So option 5 is correct. The optimal parameter vector data contains the average sale price for each type of floor material. Okay, moving on to option E. When building your models, one way to select features is to consider the pairwise relationship between each column and the response variable. Consider the following approach. So we first compute the pairwise correlation coefficient between each column and the response variable in the data frame. We sort the correlation coefficients in descending order, and we pick the top k coefficients and select the corresponding columns as the features. In 1 to 2 sentences, describe how the approach above can result in multicollinearity and issues with feature diversity. Okay, so one issue with the way that we're selecting our features right now is that if we choose, let's say, 2 features that both have a very high correlation coefficient with our response variables, the variable that we're trying to predict, it could be possible that the reason why these 2 variables have a very high correlation coefficient of the response variable is that they're closely related to one another. So these 2 variables themselves, if we calculate their correlation, they have a correlation between each other. And this means that there's multicollinearity, and this is when we have some sort of correlation between the features themselves and not just with the response variable. And this can lead to a lot of problems. For example, a very high variance in our model, because multicollinearity can cause the variance in our model to increase, and this can impact how well our model performs on unseen data such as test data. So we can say that for multicollinearity, can be present. In our features, which might lead to a high variance in our model and affect the model's performance on unseen data, such as the test set. Okay, and something else is that with this approach, there is no really feature diversity, because every single time we do this approach, we're going to just get the same correlation coefficients for all the columns. And we're just going to end up using the same fixed set of columns in our design matrix. We're never going to get a different set of columns or a different combination of columns. And this can limit our feature diversity when we build our model. So we can say that for feature diversity, it's limited because the approach always produces the same set of columns for our features. Okay, and this concludes the walkthrough for question 4.